All right, welcome back. Welcome back to classes here. Hope your Thanksgiving break was good. All right, so here's some announcements here. So last hand-in homework is due this Thursday. I put up a practice exam up on Moodle for the final, so take a look at that. Recommended problems are up on Moodle. There's an assignment due tonight on Pearson. And then you'll have your last online assignment is due next Monday. You can, of course, get that done early if you want to make sure your finals week is all clear. Third exam is on the December 12th. Let me know if you have a conflict or if you're doing 3 exams on that same day. You can get one of them switched out to a different day. But yeah, let me know this week if you have any conflicts you absolutely can't miss. Yeah, I won't do makeups for travel plans, just so you know. So make sure your travel plans are good with that. All right, any questions with any of this? All right, so let's look on Moodle for a sec here. Let me just show you some of the stuff that's up here. Yeah, so here's the recommended problems, and then we've got the different hypothesis tests. So 1, 2, and 3 of them. Those are the same ones as in the course pack, but they're well, maybe the second one's better here. So it's all written on one page though. So it's all a little more condensed if you're studying how to do hypothesis testing. And then the practice exam is near the bottom, right here, practice exam number 3. And again, you'll be given that this inference sheet, the green summary inference sheet. You'll be given a fresh one for the final, so you can look at that and get used to using that. All right. All right, so before the break, we were in the middle of a example. This was our 2-proportion hypothesis test, and it was about different CPRs. You could do CPR with just the compressions, and then you could do CPR with compressions and also the rescue breaths to try to fill up their lungs. All right, and we made it through. So we defined the parameters, and then we said what the 2 hypotheses were. We had a null hypothesis and a alternative hypothesis. That's right here. And we've got either there is no difference, so that was the null hypothesis. And the alternative hypothesis was that there was a difference. And then to verify that we can use the central limit theorem here, we need SRS with both of the groups. We need both of the sample sizes not too large, so less than 10%. We need the 2 groups to be independent from each other, so they're not affecting each other. And then also we check the success failure condition with both groups. And then after that, you want to get what the sample proportions were. So we figured that out, P hat, P1 hat and P2 hat. And this is just the successes. So the people who survived over the total. Oh, and I was looking at this and I was thinking, how did they do this as an experiment? That's why I want to know. I guess maybe it was in a hospital and they decided one or the other, just to see if there was a difference. Yeah, I was curious about that. All right, so with the pooled, we have the successes over the totals. So from group one, we had 122, and then we add the successes from the group two was 105. And now we have the totals, and I actually might be kind of handy to do this is to write the totals here. So we've got 978 and 956. So we'll add those two numbers together, and that will be our grand total for our pooled. All right, and you may be wondering why again are we able to pool these two samples together? And it's because we're assuming that the null hypothesis is true, so that there is no difference, and therefore it would be okay to mix the two samples like this. All right, and you do that, you should get point. Oh, yeah. Let me do this again. I realized I was wrong. Here, maybe one of you could see it. How do you know that this number is not right? Does anybody see why? Yeah. Right. Yeah. It should be somewhere between these, you'd think. That would make sense. So let's try to do this again. Well, let's get our parentheses. It's 105 divided by. All right, that seems a little more reasonable. Is 0.117. So this is in fact not the right one. All right. Okay, so now we have pooled standard error, and where I see that is on the inference sheet. So let's go back to here. So we're doing a test, so we're down in the bottom. And then we have two proportions, so we're right here. And then our standard error is what's in the denominator. So it's the square root of p hat pooled over q hat pooled over n1 plus p hat pooled times q hat pooled over n2. All right. So on the next page, we have that written out again. All right, so we had, it was 0.117. And then Q hat pooled is 1 minus that. 0.883. All right, and then N1 was the sample size, which was 978. And then N2 was 956. And again, we have the two pooled proportions. All right, let's stick that in our calculator. So we've got 0.117 times 0.883 divided by 978 plus 0.117 times 0.883 divided by 956. And then you get a standard error of 0.0146. All right, and then we can refer back to the summary of inference procedures. It's down here. We need to find the z-score. So now we have p1 hat minus p2 hat all over what we just found, that standard error. Right. So yeah, this green paper can really just guide you through some of these problems here. All right, so we had P1 hat of 0.125, P2 hat of 0.110. And I think I'm actually going to round this a little bit just so it's super nice. Sorry about that. Let's get this in the right spot here. So now it'll work out to be 1, just so it's super nice. All right, so now we're supposed to find the p-value. All right, with this, we have to remember, okay, so first off, this is a normal distribution. So what we draw is, I actually draw pretty much the same shape for both the t distribution and the normal distribution because they're really close to each other. But just realize that this is a normal distribution right there. All right. And let's go ahead and use our z-score. So this is a standard normal distribution. Got 0 at the center. 1, 2, 3. -1, -2, -3. So you could even write standard, normal, distribution. All right, so now our test statistic is right here at 1. And then we have to decide which way to shade. How do we shade this? So what you do is you go back to your null and alternative hypotheses. This was on, yeah, a couple pages ago. Last page, actually. There, I think that works. So we see that this is a not equal. So that tells you that you shade the extremes. You shade above and below. So it's a two-sided test. So we shade above 1 and below -1. Can anybody guess what the p-value will be off of this? Think back to the empirical rule, the 68, 95, 99.7 rule. Oh, did someone say it? Yeah, 32. Yeah, so you see, it was 68% in the middle, within one standard deviation, and then the rest would be 100 minus 68, or 32%. So that could be our guess. So yeah, again, that's the great thing about drawing pictures is you can always guess about how much is shaded in just by how you draw it. So guess 100 minus 68, 32%. All right, so let's go ahead and use the normal CDF to find the actual p-value. p-value 2 times normal CDF. And then we can just go ahead and use the right tail right here. So it starts at 1, and then it goes up to 10 to the 99th. And since this is the standard normal distribution, we don't need to specify the center or the standard standard deviation. If you do, if your calculator actually does need that, then it's a 0 and a 1. So. All right. So we've got 1, 10 to the 99th. And we get and then we have to multiply that by 2. So 0.317, or yeah. So pretty much the p-value is this shaded region. All right. So when you're interpreting the p-value, you want to describe what this shaded region is. So the difference between interpreting and making a conclusion. So interpreting, describing what the shaded region means. A conclusion, you're trying to choose either H0 or HA. So which hypothesis do you like more? Which has more evidence for it? All right, so here we've got a shaded region, so it's a probability. And then these are differences. So it's a probability of getting this difference. And since it's two-sided, we want to use the phrase as extreme as, because it could be either to the right or to the left. And then the last part is you want to make sure to mention that you're working under the null hypothesis. That's the last part to a complete answer here. Okay, so let's write this down. It gets a little wordy with the two with the two different groups. So there is a 31.7% chance of getting a difference between survival rates of CPR recipients with, and then we've got the two groups here. So with the chest compressions only, and both chest compressions and rescue breaths. And you can go ahead and give the sample sizes here. 978, 956. And then to cap it all off, we want to restate what the null hypothesis is that we're working under. So assuming, I forgot to say as extreme. Okay, so as extreme or more extreme as, and the difference was, it's actually, it was 0.125 minus 0.110. That was the difference between the two sample proportions, P1 hat and P2 hat. So that difference was 0.015. Assuming, so now we're capping it off with the null hypothesis here. Assuming that there is no difference between the two strategies. All right, so yeah, a little wordy. But yeah, the main things here are that we've got that this is a difference. We have context, so we're saying that these are CPR people that needed to get CPR, and then we say as extreme or more extreme because this is two-sided. And then this is the null hypothesis right there. All right. All right. So now the conclusion is a little easier. You just have to say one or the other. And this p-value is really high, so it's a p-value of 0.317. Gives no evidence that there is a difference between chest compressions only and both chest compressions and rescue breaths. I guess I should mention these are survival rates, difference in survival rates. Yeah, I forgot to mention that. All right. All right, so then to finish off this, this example, we've got a 95% confidence for the difference of these two parameters, P1 minus P2. And we get something that goes from negative 0.0138 to 0.0436. And the only thing you're looking for here is whether or not 0 is within this interval. And then you want to see if that matches up with what your conclusion was. So if 0 is in this interval, you think that that you'd like to stick with the null hypothesis because that the difference was 0. So that could be a very real possibility here with this confidence interval. And then to explain this, we just point that out. So you'd say since 0 is contained in this interval, there is no evidence that there is a difference. between the two CPR strategies. Oh, again, I forgot. You should write difference in survival rates, because there is a difference. One is with rescue breaths, the other is not with rescue breaths. Difference in survival rates. All right, and then I just took a new sentence here to say that it was consistent. So this is consistent with our findings from the hypothesis test. All right, any questions on any of this in this example? All right, so I thought that maybe at this point it would be nice to do an example of another example of a T distribution problem. So I'm gonna crowdsource this. Anybody have a variable that they would like to talk about, a quantitative variable? If you can think of one, just raise your hand. Yeah, so think like inches, feet, pounds, speed. Anybody have any ideas? I mean, I can think of one too. How about elephant weights? How about that? Let's do a study on elephant weights, and then we want to get a confidence interval, and then we also want to let's just do a test as well while we're at it. Okay, so this is a T distribution example. Oh yeah, while we're here, before we dive in, maybe we could just talk about what the last classes will be like. So I expect to finish out the course pack on Wednesday. And then on Friday, we'll just do some in-class review, and I'll just pick out some problems from around. Oh, and I was also thinking, I could just pose this question to you. I want to do a review like after hours, like in the evening sometime. Would you appreciate it more this week or next week? Next week? I heard a lot of next weeks. Does that give me some nods if you like next week? All right, I see a lot of nods. So let's just do it next week. Maybe we can stick with our Tuesday night plan. Tuesday night. All right, so yeah, let's plan on that. I'll set a time and we'll do that. Next announcements. Okay, so let's say we would like between 15 and 40 elephants, because that way we have enough that we can use the central limit theorem. Let's say it's probably hard to get them, so maybe 20 elephants. So we take an SRS of 20 elephants. And let's say that we have, this would be pretty elaborate, but let's say we have one of those like semi-scale that weighs how heavy semis are, and we like hide it. We hide it out there, or maybe like put some bait on there so that we can lure the elephants on there, and we can get their weights. So we get the weights of these elephants. We take an SRS of 20 elephants, and we weigh them in, let's just say kilograms. And let's say that we have, in like, let's say last year, let's say we did this last year. So last year's study, we found an average weight of, I don't know, how much do you think elephants weigh? Like 4,000 pounds, 5,000 pounds? Higher or lower? 5,000 pounds. Higher? 7,000 pounds. Higher or lower? 13,000 pounds? Sure. Yeah, let's go with it. So that would be about, 6,000 kilograms. We wonder if the elephants have gained weight. Weight this year. All right, so let's say this year we have an average of let's just say, how about 6,100 kilograms and a standard deviation of 50 kilograms. All right. And we want to decide whether or not they've gained weight. All right. So, so we want to do a test. So if we were to look here, we're like, okay, we're doing a test here. We're working with one mean, actually. It can be a little confusing here because you may think, oh, is it two means or one mean? In this case, we can assume that the study from last year is actually the average for the population. We can assume that. And then we can use a t-test here. All right. So we have, let's just define what our parameter is. So our parameter is mu, and that is the average weight, kilogram, of elephants. I suppose it'd be good to say where they are. Like, let's just say that these are African elephants. All right, so then we've got two hypotheses. We've got H naught, HA. Oh, I can't believe I did that. Okay, let's try this again. Yeah, it's a very common mistake. So we have two hypotheses, and then now we write down what they are using a colon. So the hypothesis is what follows. So what follows is some kind of a, the average is equal. Maybe it's equal to the average from last year. Mu equals 6,000 kilograms. And then the alternative, we just want to know if they gained weight. So is it more than 6,000 kilograms? All right. So now we need to find, well, we want to find a p-value eventually. So we need to know what the y bar is, and it's given here. So let's just maybe list these off. N equals 20, y bar equals 6,100 kilograms. We've got an S, so that's from the sample was 50 kilograms. And that's pretty much everything we know so far. Let's go ahead and see if we can use the central limit theorem. Let's check our conditions. So let's assume that we're able to get an SRS. And then we also don't want too many elephants. So 20 elephants is less than 10% of elephant, hopefully. Hopefully there's more than 200 elephants. And now we don't do the success failure because this isn't a proportion. We just see if it's between 15 and 40. Since n equals 20 is between 15 and 40, sample is large enough. The sample. So these are all checks right there. So we check the three conditions there. All right, so now we can draw a picture. And this is a t distribution. It has 19 degrees of freedom. 0, 1, 2, 3. So this is t distribution, 19 degrees of freedom. All right, any questions so far? Maybe I can zoom in on that little picture there. All right. So now we need to decide what the test statistic is. So recall, and this is on the green sheet here, t equals y bar minus mu naught all over s divided by square root of n. So we had a y bar was 6,100 kilograms. Mu naught is 6,000. S is 50. Square root of 20, so n was 20. Find this. $6,000 divided by 50 divided by square root of 20. Yeah, don't forget your parentheses with these. It's easy to get the parentheses mixed up and then your answer's totally off. All right, so this is an 8.944, which is just really, really, really high So it's gonna be pretty sure that they have gained weight from something like this. So this is 8.944. And that's just way out on the right. And so it's just gonna have a little sliver here shaded to the right. So let's say this is 8 right there. And then to figure that out, let's just go through the steps. At this point, I could confidently say this is going to be about a 0. Because if you get something like an 8, that's like way out, and that's hardly anything. So yeah. So we could use a. We could use a. I think we should be able to use a t-table. Yeah, let's try to use a t-table with this. I don't think it'll actually even go out far enough. Let's just look at it here. So on Moodle, there is a t-table. It's right here underneath the practice exam. And so the degrees of freedom was 19. And these are probabilities here. So this should actually be used if you have an area. If you have an area here, and you want to find what the value is. So we don't actually want to use this. Yeah, none of these are even close to 8. So let's use our calculator, and I think everybody should have this on their calculator. So it's TCDF. Everybody should have TCDF, right? So we go from 8.944 to the right, and we have 19 degrees of freedom. And you see it's 1.5 and times 10 to the negative 8. So it's really small there. So I'm just going to say the p-value is about 0. All right, and then let's write out the conclusion, and then we can have that. Does everybody see why we used a t-distribution here? I'm just curious. Yeah, everybody's good with that. Maybe I could get one of you to just summarize it real quick. Why did we use a t? Yeah. Yeah, you'll have to figure it out. Yeah, so it can be a little confusing. There's 8 choices here on the sheet here, so at least you have a 1 in 8 chance of knowing which one to do. But you can do better than that. So this was a quantitative variable, so kilograms. So that means that we were in means. We're working with means here. So we could choose. We've only got 4 of these that are about means. Means. And then we also only had one mean. And that was the, we only have one group here. It's a little iffy that there's two groups, but generally they'll say like, oh, is there a difference between these 2 groups? So it'll be obvious that you're doing a two means. You're doing a comparison there. in this case, we just have one mean. It's just we're wondering if this new study is going to be a increase or a decrease or maybe a difference. Like we don't know which direction. So the short answer is that we're given S from the sample, and we don't know what sigma is. So if you're given, if you know what sigma is, then you can just use the normal distribution. If you don't know what sigma is, so in this case, we just had S from the sample right here. That means that it's a t distribution. All right, is that kind of clear? So we can be working with proportions or means. And with the means, you've got a chance of working with the t distribution. All right. So yeah, let's just write this. I'll write this conclusion up maybe right here. So with a p-value about 0, there is very strong evidence that the elephants gained weight. All right, and let's just go ahead and end it there. We finished with our example. And we'll finish out the course pack on Wednesday. Yeah.